Introduction. Data science is an interdisciplinary field that uses scientific methods, algorithms, processes, and systems to extract knowledge and insights from structured and unstructured data. It combines elements of statistics, mathematics, computer science, and domain knowledge to analyze and interpret complex datasets. Data scientists employ various techniques such as data mining, machine learning, predictive analytics, and data visualization to uncover patterns, trends, and correlations within the data. The insights derived from data science can be used to inform decision-making, optimize processes, develop predictive models, and drive innovation across industries ranging from healthcare and finance to marketing and manufacturing. The history of data science can be traced back to the early days of statistics and computer science, but its emergence as a distinct field is relatively recent. Here's a brief overview. Early foundations, before 20th century. The roots of data science can be found in disciplines such as statistics, mathematics, and computer science. Early statisticians like Sir Ronald Fisher and Carl Pearson laid the groundwork for statistical analysis and hypothesis testing. Meanwhile, developments in computer science, particularly in algorithms and programming languages, set the stage for handling large datasets. Statistics and computational era, 20th century. During the 20th century, statistics became increasingly important for making data-driven decisions in various fields such as agriculture, economics, and sociology. With the advent of computers, computational techniques became integral to statistical analysis, enabling the processing of larger datasets and the development of more complex models. Data warehousing and business intelligence, 1970s, 1990s. The rise of relational databases and data warehousing in the 1970s paved the way for storing and managing large volumes of data. In the 1990s, the emergence of business intelligence (BI) tools enabled organizations to analyze historical data to gain insights into their operations and performance. Big data era, 2000s. The proliferation of the internet, social media, and digital devices led to an explosion of data generation. This era saw the emergence of big data technologies and platforms capable of processing and analyzing massive datasets that traditional relational databases couldn't handle efficiently. Technologies like Hadoop and MapReduce became popular for distributed computing and processing large-scale data. Rise of data science, 2010s, present. The term data science gained prominence in the early 2010s as organizations recognized the need for professionals with a diverse skill set to extract insights from data. Data science incorporates elements of statistics, machine learning, computer science, and domain expertise to analyze complex datasets and make data-driven decisions. With the increasing availability of data and advancements in machine learning algorithms and computational power, data science has become essential across various industries. Current trends and future directions. As of my last update in January 2022, data science continues to evolve rapidly. Emerging trends include the integration of artificial intelligence, AI, and deep learning techniques, the adoption of cloud-based platforms for data storage and analysis, the focus on privacy and ethics in data handling, and the growing importance of interdisciplinary collaboration in solving complex data-related challenges. Overall, the history of data science reflects the convergence of statistical principles, computational techniques, and technological advancements to extract actionable insights from data and drive innovation in various domains. A brief history of machine learning. Machine learning, a subset of artificial intelligence, has roots dating back to the mid-20th century. Here's a brief history. Early concepts, 1950s, 1960s. The field of machine learning emerged from the intersection of computer science and statistics. Pioneers like Alan Turing and Marvin Minsky laid some foundational concepts. Turing proposed the idea of a learning machine in 1950. Rise of neural networks, 1940s-1970s. Inspired by the structure of the human brain, artificial neural networks, ANNs, were developed. The perceptron, one of the earliest neural network models, was created by Frank Rosenblatt in 1957. Symbolic AI dominance, 1960s-1980s. During this period, symbolic AI, which uses logical rules to manipulate symbols, was predominant. Machine learning faced setbacks due to limitations in computational power and data availability. Connectionism resurgence, 1980s-1990s. Interest in neural networks resurged with the development of backpropagation, an algorithm for training multilayer perceptrons. This led to significant advancements in pattern recognition and other domains. Support vector machines, 1990s. Vladimir Vapnik and Corinna Cortès introduced support vector machines, SVMs, a powerful algorithm for classification and regression tasks. SVMs gained popularity due to their strong theoretical foundations. Big data era, 2000s-2010s. The proliferation of the Internet led to a massive increase in data generation, enabling the training of more complex machine learning models. Techniques like deep learning, which involves training deep neural networks with many layers, became feasible due to the availability of large datasets and computational resources. Deep learning revolution, 2010s present. Deep learning techniques, particularly convolutional neural networks, CNNs, for image recognition and recurrent neural networks, RNNs, for sequential data, have achieved remarkable success in various applications such as computer vision, natural language processing, and speech recognition. Advancements in reinforcement learning, 2010s. Present. Reinforcement learning, a branch of machine learning concerned with decision-making and control, has seen significant advancements, particularly with algorithms like deep Q networks, DQN, and deep reinforcement learning. AI in the industry, 2010s. Present. Machine learning and AI have become integral parts of many industries, including healthcare, finance, transportation, and entertainment. Companies utilize machine learning for tasks such as personalized recommendations, fraud detection, and autonomous driving. Ethical and societal implications. With the increasing integration of AI into society, ethical considerations regarding bias, privacy, and job displacement have become prominent. Efforts to address these concerns and develop responsible AI systems are ongoing. Machine learning continues to evolve rapidly, driven by advancements in algorithms, data availability, and computing power, promising further breakthroughs and applications in the future. The perceptron is one of the simplest types of artificial neural networks, inspired by the biological neuron's structure and functionality. It was developed by Frank Rosenblatt in 1957. The perceptron is a single-layer neural network that can be used for binary classification tasks, such as determining whether an input belongs to one class or another. Here's how the perceptron works. Inputs. The perceptron receives input signals, each of which is multiplied by a corresponding weight. These inputs and weights represent the features of the data being processed. Summation. The weighted inputs are summed together with a bias term. Mathematically, this is represented as the dot product of the input vector and the weight vector plus the bias. Activation. The sum is then passed through an activation function, often a simple threshold function. If the sum exceeds a certain threshold, the perceptron outputs a value representing one class, otherwise it outputs the other class. Training. The perceptron learns by adjusting its weights based on the errors it makes during training. The weights are updated to reduce the difference between the predicted output and the true output for each training example. This process is typically accomplished using a technique called the perceptron learning rule, which adjusts the weights in the direction that reduces the error. Perceptrons have limitations, such as their inability to learn nonlinear patterns and their sensitivity to the choice of activation function. However, they laid the groundwork for more advanced neural network architectures, such as multilayer perceptrons and deep neural networks, which can learn complex patterns and relationships in data. The perceptron model typically consists of a single layer, known as the input layer, and an output layer. It does not have any hidden layers. Therefore, a perceptron is considered a single-layer neural network. The lack of hidden layers distinguishes the perceptron from more complex neural network architectures, such as multilayer perceptrons, MLPs, or deep neural networks, DNNs, which include one or more hidden layers between the input and output layers. These hidden layers enable the network to learn more complex patterns and relationships in the data. Multilayer perceptrons, MLPs, and deep neural networks, DNNs, are both types of artificial neural networks used in machine learning and deep learning. While they share similarities, there are also key differences between them. Depth. MLPs have at least one hidden layer between the input and output layers. They can have multiple hidden layers, but they are still relatively shallow compared to DNNs. DNNs are characterized by their depth, meaning they have multiple hidden layers stacked between the input and output layers. They typically have more layers compared to MLPs. Representation power. MLPs can learn complex patterns in data, but may struggle with very high-dimensional or nonlinear datasets. They are effective for a wide range of tasks, but may not generalize well to extremely complex problems. DNNs have significantly greater representation power due to their deeper architecture. They are capable of learning intricate and abstract features from data, enabling them to tackle more complex tasks and datasets. DNNs excel in tasks such as image recognition, natural language processing, and speech recognition. Training complexity. MLPs. Training MLPs is typically less computationally intensive compared to training DNNs. However, as the number of hidden layers or neurons increases, training time and complexity may also increase. DNNs. Training DNNs, especially very deep networks, can be computationally demanding and require substantial resources, including powerful hardware and large datasets. Techniques like stochastic gradient descent with backpropagation and regularization methods are commonly used to train DNNs effectively. Overfitting. MLPs are susceptible to overfitting, especially when dealing with complex datasets or insufficient training data. Regularization techniques such as dropout and weight decay are often used to mitigate overfitting in MLPs. DNNs, especially deep networks, are prone to overfitting due to their high capacity for learning intricate details from the data. Regularization techniques and other strategies, such as batch normalization and early stopping, are essential for preventing overfitting in DNNs. In summary, while MLPs and DNNs are both neural network architectures used for supervised learning tasks, DNNs stand out for their depth, increased representation power, and ability to handle complex datasets and tasks. However, they also come with challenges related to training complexity and overfitting, which need to be carefully addressed during model development and training. The list of algorithms. Providing a full list of machine learning algorithms is challenging because the field of machine learning is vast and continuously evolving, with new algorithms and variations being developed regularly. However, I can give you a broad overview of some of the most widely used and well-known machine learning algorithms across different categories. Linear regression, logistic regression, decision trees, random forests, support vector machines, SVM, k-nearest neighbors, KNN, naive Bayes, gradient boosting machines, GBM, neural networks, including multilayer perceptrons. Unsupervised learning algorithms. K-means clustering, hierarchical clustering, Gaussian mixture models, GMM, principal component analysis, PCA, independent component analysis, ICA, T-distributed stochastic neighbor embedding, TSNE, autoencoders. Reinforcement learning algorithms, Q-learning, deep Q networks, DQN, policy gradient methods, actor-critic methods, proximal policy optimization, PPO, deep deterministic policy gradient, DDPG. Dimensionality reduction algorithms, principal component analysis, PCA, singular value decomposition, SVD, independent component analysis, ICA. Deep learning algorithms, convolutional neural networks, CNN, recurrent neural networks, RNN, long short-term memory, LSTM. Data classification. Numerical data are numbers and can be split into two numerical categories. Discrete data, counted data that are limited to integers, example, the number of cars passing by. Discrete data is often analyzed using methods such as frequency distributions, histograms, bar charts, and probability distributions. It is distinct from continuous data, which can take any value within a certain range and is often measured, such as height, weight, temperature, etc. Continuous data. Measured data that can be any number. Example, the price of an item or the size of an item. Categorical data are values that cannot be measured up against each other. Example, a color value or any yes/no values. Ordinal data are like categorical data, but can be measured up against each other. Example, school grades where A is better than B and so on. In machine learning, data types play a crucial role in representing and manipulating the input features and target variables of a dataset. Here are some common data types encountered in machine learning. 1. Numeric data types. Continuous numeric. These are continuous numerical values, such as real numbers representing measurements like height, weight, temperature, etc. Discrete numeric. These are discrete numerical values, typically integers, representing counts or categories. Examples include counts of items, categorical codes, etc. 2. Categorical data types. Nominal. Nominal categorical data represents categories with no inherent order or ranking. Examples include color, gender, country, etc. Ordinal. Ordinal categorical data represents categories with a clear order or ranking. Examples include ratings, for example, 1-star, 2-star, 3-star, educational levels, for example, high school, bachelor's, master's, etc. 3. Text data types. Text. Text data represents textual information such as reviews, comments, documents, etc. Text data often requires pre-processing steps like tokenization, vectorization, for example, TF, IDF, word embeddings, etc., before being used in machine learning models. 4. Time series data types. Temporal. Time series data represents data points collected at successive, equally spaced intervals over time. Examples include stock prices, weather data, sensor data, etc. 5. Image data types. Images. Image data represents visual information, typically in the form of pixels arranged in a grid. Image data requires specialized pre-processing techniques like normalization, resizing, data augmentation, etc., before being fed into machine learning models. 6. Audio data types. Audio. Audio data represents sound signals, often in the form of waveform data. Audio data may require pre-processing steps like feature extraction, for example, MFCCs, spectrogram generation, etc., before being used in machine learning models. 7. Spatial data types. Spatial. Spatial data represents geographic or spatial information such as coordinates, shapes, maps, etc. Spatial data may require specialized pre-processing techniques for feature engineering and spatial analysis. 8. Mixed data types. Mixed. Datasets may contain a mix of different data types, such as numerical, categorical, text, etc. Handling mixed data types often requires careful pre-processing and feature engineering techniques tailored to the specific dataset and machine learning task. Understanding the data types present in a dataset is essential for selecting appropriate pre-processing techniques, feature engineering strategies, and machine learning algorithms that are well suited for the data at hand. Additionally, handling different data types effectively can significantly impact the performance and interpretability of machine learning models. Mean, median, and mode. The mean, median, mode, and range are averages used to analyze data. Mean, the average value. To calculate the mean, find the sum of all values and divide this sum by the number of all values. Use the NumPy mean method to find the average. The median value is the value in the middle after you have sorted all the values. If there are two numbers in the middle, divide the sum of those numbers by 2. Use the NumPy median method to find the middle value. The mode value is the value that appears the most number of times. Use the SciPy mode method to find the number that appears the most. From SciPy import stats. Range is the difference between the lowest and the highest value. To work it out, simply subtract the lowest value from the highest. Standard deviation. Standard deviation is a number that describes how spread out the values are. A low standard deviation means that most of the numbers are close to the mean, average value. A high standard deviation means that the values are spread out over a wider range. Use the NumPy STD method to find the standard deviation. Variance is another number that indicates how spread out the values are. If you take the square root of the variance, you will get the standard deviation. To calculate the variance, you have to do the following. 1. Find the mean. 2. For each value, find the difference from the mean. 3. For each difference, find the square value. The variance is the average number of these square differences. Use the NumPy var method to find the variance. Standard deviation is often represented by the symbol sigma. Variance is often represented by the symbol sigma squared. Percentiles. In statistics, a k-percentile, also known as percentile score or centile, is a score below which a given percentage k of scores in its frequency distribution falls, or a score at or below which a given percentage falls. Percentiles are expressed in the same unit of measurement as the input scores, not in percent. For instance, if the scores refer to human weight, the corresponding percentiles will be expressed in kilograms or pounds. Percentiles are statistical measures used to describe the distribution of a dataset. They divide a set of observations into 100 equal parts, with each part representing a percentile. The percentile indicates the value below which a given percentage of observations fall. For example, if you score in the 90th percentile on a standardized test, it means you performed better than 90% of the people who took the test. Percentiles are commonly used in various fields such as education, finance, healthcare, and demographics to understand the distribution of data and make comparisons between different groups or individuals. They are particularly useful for comparing data sets of different sizes or distributions. Percentiles are a type of quantiles obtained adopting a subdivision into 100 groups. The 25th percentile is also known as the first quartile, the 50th percentile as the median or second quartile, and the 75th percentile as the third quartile. Example: let's say we have an array of the ages. What is the 70 percentile? The answer is 33, meaning that 70% of the people are 33 or younger. Use the NumPy percentile method to find the percentiles. Percentile method takes two parameters, array and a number, for example, ages and 75. Physicians often use children's weight and height to evaluate their growth in comparison to national averages and percentiles which are found in growth charts. The 85th percentile speed of traffic on a road is often used as a guideline in setting speed limits and assessing whether such a limit is too high or low. 5. In finance, value at risk is a standard measure to assess the quantity under which the value of the portfolio is not expected to sink within a given period of time. Data distribution. In machine learning, understanding data distribution is crucial as it directly impacts the performance and behavior of various algorithms. Data distribution refers to the way data points are spread or arranged within a dataset. Different types of data distributions have different implications for the choice and performance of machine learning models. Here are some common types of data distributions. Normal distribution, Gaussian distribution. This is the most well-known distribution where data is symmetrically distributed around the mean, forming a bell-shaped curve. Many statistical methods and machine learning algorithms assume normal distribution, such as linear regression, logistic regression, and linear discriminant analysis. Uniform distribution. In a uniform distribution, all data points have equal probability of occurrence within a given range. Uniform distributions are common in synthetic datasets and can be useful for some types of simulations. Skewed distribution. Skewed distributions are asymmetrical distributions where the data points cluster more on one side of the distribution than the other. There are two types of skewness: positive skew, long tail to the right, and negative skew, long tail to the left. Many real-world datasets exhibit skewed distributions, such as income distribution and click-through rates. Multimodal distribution. Multimodal distributions have multiple peaks or modes, indicating that the data is composed of multiple subpopulations or clusters. Clustering algorithms and mixture models are commonly used for analyzing multimodal distributions. Exponential distribution. In an exponential distribution, the probability of an event occurring decreases exponentially as the value increases. Exponential distributions are commonly encountered in survival analysis and queuing theory. Power law distribution. Power law distributions exhibit a relationship between two quantities where one quantity varies as a power of another. Power law distributions are commonly observed in natural phenomena such as the distribution of city sizes, the frequency of word usage, and the distribution of wealth. Understanding the distribution of your data is important for selecting appropriate pre-processing techniques, feature engineering strategies, and machine learning algorithms. For example, Skewed data might require transformations, such as logarithmic or square root transformations, to make it more normally distributed, while multimodal data might require clustering or mixture models to effectively capture its underlying structure. Additionally, certain algorithms might perform better or worse depending on the distribution of the data they are trained on. Therefore, analyzing and understanding the data distribution is a crucial step in the machine learning pipeline. To create big data sets for testing, you can use the Python module NumPy, which comes with a number of methods to create random data sets of any size. Let's review these methods. 1. Random.normal. Draw random samples from a normal, Gaussian distribution. The probability density function of the normal distribution is often called the bell curve because of its characteristic shape. The normal distribution is the distribution where the values are concentrated around a given value. The normal distributions occurs often in nature. For example, it describes the commonly occurring distribution of samples influenced by a large number of tiny, random disturbances. All manner of things appear to be distributed normally: people's heights, sizes of snowflakes, errors in measurements, lifetimes of light bulbs. Random.normal accepts three parameters: mean, center of the distribution, standard deviation, spread or width of the distribution, and size, output shape. 2. Random.uniform. Draws samples from a uniform distribution. It accepts three parameters: lower boundary of the output interval, upper boundary of the output interval, size, or output shape. The continuous uniform distributions or rectangular distributions are a family of symmetric probability distributions. Such a distribution describes an experiment where there is an arbitrary outcome that lies between certain bounds. To visualize the dataset, you can draw a histogram with the data collected. Matplotlib.pyplot has a method hist and show. The method hist accepts two parameters: the array and the number of bars. Linear regression. Linear regression is a statistical method used to model the relationship between a dependent variable and one or more independent variables. It assumes that there is a linear relationship between the independent variables, also called predictor variables, and the dependent variable, also called the response variable. There are several methods to estimate the parameters, coefficients of a linear regression model. Some of the most common methods include ordinary least squares, OLS. This is the most widely used method for estimating the parameters of a linear regression model. In OLS, the parameters are estimated by minimizing the sum of squared differences between the observed and predicted values of the dependent variable. This method provides unbiased estimators if the assumptions of the linear regression model are met. Gradient descent. Gradient descent is an optimization algorithm used to minimize the error function, for example, the sum of squared errors, by iteratively adjusting the parameters of the model. It starts with initial parameter values and updates them in the direction that reduces the error until convergence is reached. Gradient descent can be used for linear regression when the dataset is too large for OLS or when the cost function is non-convex. Analytical methods. Some linear regression models have closed-form solutions that allow for direct computation of the parameter estimates. For example, in simple linear regression with one independent variable, the coefficients can be calculated analytically using formulas. However, such analytical solutions may not be feasible for more complex regression models. Matrix inversion. Linear regression can also be solved using matrix algebra. The parameter estimates can be obtained by solving the normal equations, which involve matrix operations such as matrix multiplication and inversion. This method is commonly used in statistical software packages for estimating linear regression models. Iterative methods. Iterative methods, such as the Gauss-Newton algorithm or the iteratively reweighted least squares (IRLS) algorithm, are used when dealing with nonlinear regression models or when the assumptions of linear regression are violated. These methods iteratively update the parameter estimates until convergence is achieved. Regularization techniques. Regularization methods such as ridge regression, L2 regularization, and lasso regression, L1 regularization, are used to prevent overfitting and improve the generalization of linear regression models. These methods add a penalty term to the cost function, which encourages simpler models by shrinking the coefficients towards zero. These are some of the main methods used to estimate the parameters of linear regression models. The choice of method depends on factors such as the size of the dataset, computational resources, model complexity, and specific requirements of the analysis. Linear regression is widely used in various fields such as economics, finance, biology, engineering, and social sciences for modeling and predicting continuous outcomes. However, it's important to note that linear regression makes several assumptions, including linearity, independence of errors, constant variance of errors, and normally distributed errors. Violations of these assumptions can affect the accuracy and reliability of the model's predictions. Multiple regression is a statistical technique used to analyze the relationship between multiple independent variables and a single dependent variable. It extends the principles of simple linear regression, which involves just one independent variable and one dependent variable, to situations where there are multiple predictors. In multiple regression, the goal is to create a linear model that best predicts the value of the dependent variable based on the values of the independent variables. The model equation is typically represented as y equals b0 plus b1 by 1 plus b2 by 2 plus b3 by 3, etc. Y is the dependent variable. x1, x2, x3 are independent variables. b0 is S the intercept, constant term. b1, b2, b3 are the coefficients, regression weights, that represent the change in the dependent variable. The coefficients are estimated from the data using methods like ordinary least squares, OLS regression. The quality of the model fit is typically assessed using metrics like R-squared, coefficient of determination, adjusted R-squared, and significance tests for the coefficients. Multiple regression is widely used in various fields, including economics, social sciences, psychology, and natural sciences, for modeling complex relationships between variables and making predictions based on those relationships. Ordinary least squares, OLS regression, is a method used to estimate the parameters of a linear regression model by minimizing the sum of the squared differences between the observed and predicted values of the dependent variable. In other words, it finds the line, or plane in the case of multiple regression, that best fits the data points. The basic idea behind OLS regression is to find the values of the coefficients, regression weights, that minimize the sum of the squared residuals, where the residual is the difference between the observed value of the dependent variable and the value predicted by the regression model. To calculate multiple regression, import linear model from a Python module Sklearn. Linear model has a method linear regression, which returns object that has two methods, fit and predict. Polynomial regression is a type of regression analysis in which the relationship between the independent variable x and the dependent variable y is modeled as an n-degree polynomial. In simple linear regression, we model the relationship between x and y as a straight line, while in polynomial regression, we allow for curves in the relationship. The degree of the polynomial n determines the complexity of the curve that can be fitted to the data. For example, if n equals 2, the regression equation is quadratic, n equals 3 makes it cubic, and so on. Performing polynomial regression involves estimating the coefficients that best fit the observed data. This can be done using methods like the method of least squares or maximum likelihood estimation. Polynomial regression can capture nonlinear relationships between variables better than simple linear regression. However, higher-degree polynomials can sometimes lead to overfitting, where the model fits the training data too closely and performs poorly on unseen data. Regularization techniques like ridge regression or lasso regression can help mitigate overfitting in polynomial regression models. To perform polynomial regression, the data is first plotted and analyzed to determine the best-fitting polynomial equation. The polynomial regression model is then trained by adjusting the coefficients of the polynomial terms to minimize the difference between the observed and predicted values of the dependent variable. The resulting equation can then be used to make predictions for new data. NumPy module has such methods to implement this type of regression: polyfit and poly1D. It is necessary to know how good the relationship between the values of the x and y axis is if there are no relationship. The polynomial regression should not be used to predict anything. The relationship can be measured with a value called the r-squared. The r-squared value ranges from 0 to 1. 0 means no relationship, and 1 means 100% related. Sklearn module has a method R2 which can compute this value. It accepts two parameters, y and a model. Practical uses of polynomial regression. Polynomial regression finds itself an important tool in real-world analytics. For example, economic growth modeling, climate change, healthcare. Healthcare data analyzing often resorts to polynomial regression. It is useful to predict disease trends. Logistic regression, k-nearest neighbors, KNN, and random forest are all popular machine learning algorithms used for classification tasks. Here's a brief overview of each. Logistic regression. Logistic regression is a linear model used for binary classification problems. It models the probability that a given input belongs to a particular class using the logistic function, sigmoid function. Despite its name, logistic regression is a classification algorithm rather than a regression algorithm. It's simple, interpretable, and works well when the relationship between features and target variable is linear. K, nearest neighbors, KNN. KNN is a non-parametric lazy learning algorithm used for classification and regression tasks. It classifies a data point based on the majority class of its k nearest neighbors. The value of k is a hyperparameter that needs to be tuned. Smaller values of k tend to overfit, while larger values may underfit. KNN doesn't build a model during training. Instead, it memorizes the training data. Random forests. Random forests is an ensemble learning method based on decision trees. It builds multiple decision trees during training and combines their predictions through voting or averaging for classification tasks. Random forests introduce randomness during training by bootstrapping the data and randomly selecting a subset of features at each split. They are robust against overfitting and handle high-dimensional data well. Random forests can also provide feature importance, which helps in understanding the most influential features in the dataset. Each of these algorithms has its strengths and weaknesses, and the choice between them depends on the nature of the data, the problem at hand, and computational considerations. For instance, use logistic regression for linearly separable data or when interpretability is important. Use KNN when the decision boundary is nonlinear and the dataset is not too large. Use random forests when you want a robust model that handles high-dimensional data and provides feature importance. In practice, it's common to try multiple algorithms and compare their performance using techniques like cross-validation to select the best one for a particular task. In machine learning, the process of training and testing is fundamental for building and evaluating predictive models. Here's an overview of each step. Training. Training refers to the process of using a dataset to teach a machine learning model how to make predictions. During training, the model learns the patterns and relationships present in the training data. The training data typically consists of input features, independent variables, and corresponding target labels, dependent variable. The model adjusts its parameters, weights, and biases based on the training data in order to minimize the difference between its predictions and the actual target values. The goal is to create a model that can generalize well to unseen data. Testing, evaluation. Testing, also known as evaluation or validation, is the process of assessing the performance of a trained model on unseen data. A separate dataset, called the test set or validation set, is used for this purpose. The test set contains examples that the model hasn't seen during training. The model makes predictions on the test set, and its performance is evaluated by comparing these predictions to the actual target labels. Common evaluation metrics include accuracy, precision, recall, F1 score, and area under the ROC curve, AUC ROC, among others. The choice of evaluation metric depends on the specific problem and requirements. It's important to split the dataset into training and test sets to ensure an unbiased evaluation of the model's performance. This helps to assess how well the model generalizes to new, unseen data. Typically, the data is randomly divided into two subsets, a larger portion for training, for example, 70 to 80% of the data, and a smaller portion for testing, for example, 20 to 30% of the data. In some cases, particularly when working with smaller datasets, techniques like cross-validation, for example, K-fold cross-validation, are used to ensure more robust evaluation by systematically splitting the data into multiple trained test pairs. This helps to reduce the variance in performance estimates and provides a more reliable assessment of the model's capabilities. Cross-validation and confusion matrix are two essential techniques in machine learning for model evaluation and performance assessment. Cross-validation. Cross-validation is a resampling technique used to assess how well a predictive model generalizes to an independent dataset. It involves partitioning the original dataset into multiple subsets, folds, where one subset is retained as the validation set and the rest are used for training. This process is repeated multiple times, with each fold serving as the validation set exactly once. The performance of the model is then averaged over all folds to obtain a more robust estimate of its performance. One of the most common types of cross-validation is K-fold cross-validation, where the dataset is divided into K equal-sized folds. Other variations include stratified K-fold cross-validation, leave-one-out cross-validation, and nested cross-validation. Confusion matrix. A confusion matrix is a table that summarizes the performance of a classification model on a set of test data. It provides a detailed breakdown of the model's predictions compared to the actual class labels. The matrix is organized into rows and columns, where the rows represent the actual classes and the columns represent the predicted classes. The four cells of the confusion matrix are: true positive TP. The model correctly predicted instances of the positive class. True negative TN. The model correctly predicted instances of the negative class. False positive FP. The model incorrectly predicted instances of the positive class as negative. False negative FN. the model incorrectly predicted instances of the negative class as positive. From the confusion matrix, various evaluation metrics can be derived, such as accuracy, precision, recall, sensitivity, specificity, F1 score, and the area under the ROC curve, AUC ROC. These metrics provide insights into different aspects of the model's performance, such as its ability to correctly identify positive and negative instances, and its overall effectiveness in classification tasks. Both cross-validation and confusion matrix play crucial roles in assessing the performance of machine learning models and are commonly used in conjunction with each other to obtain a comprehensive understanding of model behavior and generalization capabilities. Python offers a rich ecosystem of libraries and modules for machine learning, making it one of the most popular languages for ML development. Here are some of the most widely used Python libraries for machine learning. Scikit-learn. Scikit-learn is a powerful library for machine learning in Python. It provides simple and efficient tools for data mining and data analysis. Includes various algorithms for classification, regression, clustering, dimensionality reduction, model selection, and preprocessing. Offers extensive documentation and tutorials, making it suitable for both beginners and experienced users. TensorFlow. TensorFlow is an open-source machine learning framework developed by Google Brain. It provides a comprehensive ecosystem of tools, libraries, and community resources for building and deploying ML models. TensorFlow supports both deep learning and traditional machine learning techniques. It allows for flexible model building using high-level APIs like Keras or lower-level APIs for more fine-grained control. PyTorch. PyTorch is another popular deep learning framework developed by Facebook AI Research. Known for its dynamic computation graph, which enables more intuitive model building and debugging. Offers extensive support for GPU acceleration, making it suitable for training large-scale deep learning models. Provides a rich set of tools and libraries for neural networks, optimization, and automatic differentiation. Keras. Keras is a high-level neural networks API written in Python and capable of running on top of TensorFlow, Theno, or Microsoft Cognitive Toolkit, CNTK. It allows for easy and fast prototyping of deep learning models, designed for enabling fast experimentation with deep neural networks. XGBoost. XGBoost is an optimized gradient boosting library that provides a highly efficient implementation of gradient boosting machines, widely used for classification and regression tasks. Offers support for various objective functions, tree-based algorithms, and regularization techniques. LightGBM. LightGBM is a gradient boosting framework developed by Microsoft. It's known for its high efficiency, low memory usage, and speed. Particularly effective for large-scale and distributed machine learning tasks. Pandas. Pandas is a versatile data manipulation and analysis library in Python. Provides data structures like data frame and series, which are essential for data preprocessing and exploration. Integrates well with other machine learning libraries like Scikit-learn. NumPy. NumPy is the fundamental package for scientific computing with Python. Provides support for multidimensional arrays and matrices, along with a collection of mathematical functions to operate on these arrays. Used extensively for numerical operations in machine learning algorithms. These libraries form the backbone of many machine learning projects in Python, offering a wide range of functionalities for data preprocessing, model development, evaluation, and deployment. Depending on the specific requirements of your project, you may choose to use one or more of these libraries in combination. In addition to specific Python libraries for machine learning, there are various data science tools and platforms that offer comprehensive environments for data analysis, visualization, and machine learning. Here are some popular ones. Jupyter Notebook. Jupyter Notebook is an open-source web application that allows you to create and share documents containing live code, equations, visualizations, and narrative text. It supports various programming languages, including Python, R, and Julia. Jupyter Notebooks are widely used for exploratory data analysis, prototyping machine learning models, and sharing research findings. RStudio. RStudio is an integrated development environment, IDE, for the R programming language. It provides a user-friendly interface for R programming, data visualization, and statistical analysis. RStudio supports features like syntax highlighting, code execution, debugging, and package management. Apache Spark. Apache Spark is an open-source distributed computing system designed for big data processing and analytics. It provides a unified analytics engine for large-scale data processing, machine learning, and graph processing. Spark's core abstraction is the Resilient Distributed Dataset, RDD, which allows for fault-tolerant parallel processing of data. Tableau. Tableau is a powerful data visualization tool that allows users to create interactive and shareable dashboards and reports. It supports a wide range of data sources and offers intuitive drag-and-drop functionality for creating visualizations. Tableau is popular among data analysts and business users for its ease of use and advanced visualization capabilities. Microsoft Power BI. Microsoft Power BI is a business analytics tool that provides interactive visualizations and business intelligence capabilities. It allows users to connect to various data sources, transform data, and create interactive dashboards and reports. Power BI integrates well with other Microsoft products like Excel and Azure, making it suitable for enterprise use. KNIME. KNIME is an open-source data analytics platform that allows users to create visual workflows for data pre-processing, analysis, and modeling. It provides a wide range of built-in tools and integrations with other data science libraries and platforms. KNIME supports both GUI-based and scripting-based workflows, making it suitable for users with different levels of programming experience. RapidMiner. RapidMiner is an integrated data science platform that offers a visual environment for building, validating, and deploying predictive models. It provides a drag-and-drop interface for data pre-processing, feature engineering, and model building. RapidMiner supports a wide range of machine learning algorithms and offers automation capabilities for building end-to-end data science pipelines. These tools and platforms provide comprehensive environments for various aspects of data science, including data manipulation, visualization, statistical analysis, and machine learning. Depending on your specific requirements and preferences, you can choose the tool that best fits your needs.